Hello, I'm Alessandra Merlotti and I'm a postdoc at the University of Bologna in Italy, and I am one of the researchers who collaborate on the Genigma project. In my research activity, I study the properties of genomic sequences through network and statistical methods. And in this presentation, I will show you how the game works. In particular, we will see which properties of high-C data we can use to assign a score to each configuration of the sequence, and what tools the game offers to efficiently identify the optimal solution. Let's understand how the game works. As Mark and Juan showed us before, there is a hierarchy among the contacts measured through a high-C experiment that can be easily visualized by representing the data in matrix form. In fact, as you can see from this contact map, the frequency of interactions between DNA fragments decreases as we move away from the diagonal. This particular property of high-C matrices tells us that the higher the number of contacts between pairs of fragments, the closer they are along the sequence. Therefore, to correctly reconstruct the sequence, we must move the DNA fragments, that in the game will be represented by these colored bricks, in such a way that the closest ones will be those between which we observed the highest number of contacts. In fact, in the case of a configuration where the fragments are correctly ordered, the expected trend is similar to the one that is shown in this example, in which the values of the contacts between adjacent fragments along the sequence, such as AB, BC, CD, and DE, are on average the highest if compared to those between more distant fragments, such as AC, BD, C, and so on. This property of high-C matrices allows to define a criterion that we can use to measure the goodness of the sequence reconstruction, and thus to associate a score to each configuration that in the game will be shown here. The game, in fact, penalizes configurations in which pairs of distant fragments have a high number of contacts, assigning them a lower score, as shown in these two examples. On the left, we have the correct configuration, where the hierarchy of the contact is respected. On the right, we have an incorrect configuration with a lower score, since the hierarchy of the contacts is not respected. The aim of the game is to identify the correct order of the DNA fragments. In other words, we have to identify the configuration that produces the highest possible score. Therefore, if we imagine that we are moving in a space like the one represented in this slide, in which each step corresponds to a possible configuration of the sequence, we can represent the player section as a ball, jumping from one step to another, starting from an initial configuration. The jump will be determined by the movement of one or more fragments within the game, and the aim will be to reach lower and lower steps, corresponding to configurations with higher and higher scores. What we expect is that in regions of the sequence where there are no rearrangements, the order of the fragments corresponding to the configuration with the maximum score is the same as in the reference genome. But we know that in cancer cells there are also regions of the sequence where we can find rearrangements, and in this case we expect that the order of the fragments is different from that of the reference genome, whose configuration will therefore have a lower score than the one identified by the game as optimal. At this point, we can ask ourselves, how many DNA configurations can we explore with the game? The answer is, it depends on the difficulty of the level that we are playing at. In fact, the game is divided into 3 levels: easy, intermediate, and difficult. The more games you will solve, the faster you will move from one level to another. In particular, in the easy level, the player will have to rearrange 8 DNA fragments, which correspond to 4 times 10 to the 4th configurations. In the intermediate level, the player will have to order 16 fragments, which correspond to 2 times 10 to the 13th configurations. In the difficult level, the player will have to rearrange 35 fragments, which correspond to about 10 to the 30th configurations. As you can see, the number of configurations that we can explore grows rapidly as the number of fragments increases. Therefore, we will have to adopt a strategy that allows an efficient search for the best solution. To do this, we will use our eyes and the ability of our brain to quickly process visual stimuli, because, as we say in Genigma, my eye is better than artificial intelligence. Therefore, the challenge is, can we do better than the algorithm? For example, what the algorithm can do in the easier levels is to explore all the possible configurations and choose the one with the highest score. On the contrary, the game wants to make the search more efficient, providing tools that guide the player's eye in order to avoid a forced exploration of all the possible combinations. And this is done, first of all, through colors. In fact, the fragments can take on 4 colors, ranging from red, which indicates the worst positioned fragments, to green, which indicates the best positioned fragments. However, it may happen that we reach configurations where all the fragments have the same color. In this case, we can use the score associated with each brick. The higher the number, the better the position of the fragment within the sequence. To give an idea of how this indicator works, let's have a look at these screenshots taken at different moments of the game. You can see how, from left to right, the pieces change their positions, giving rise to different configurations of the sequence. In particular, we have configurations with higher and higher scores. That means better and better configurations, in which the color of the fragments changes from warmer to colder shades, and the score associated with each fragment increases its value. But we will face the real biggest challenge in the difficult level, where we have to order 35 fragments. In this case, in fact, we have many configurations to explore. Therefore, the algorithm, to be efficient, changes strategy and drastically reduces the number of configurations to be explored, carrying out a local search for the best movement step by step, without taking into account the entire hierarchy of contacts among the fragments. This means that, in most of the cases, the algorithm cannot reach the best configurations, leaving unexplored many others with higher score. What we want to do with Genigma is to reach these configurations and find the best one. However, since we don't know a priori the maximum value of the score that we can reach, we will use the consensus criterion to define which is the best configuration, requiring that at least 40 players identify the same solution with the highest score. In this way, the genome organization provided by the game will be the result of a collective solution that reflects the consensus of the players. Of course, to win this challenge, we need everyone's contribution. Therefore, we invite you to collaborate in council research and play Genigma. Thank you very much for your attention.